All right, so we're in section 9.5 now, and we're looking at alternating series. So far we've been looking at series with all positive terms. So alternating series, we have series with both positive and negative terms, and they can occur in alternating series occur in two different ways. Our even terms can be negative, or our positive terms can be negative. Just depends on how we set up our alternating signs, but they can end up they occur in two ways. So our test for convergence for alternating series is our alternating series test. And our alternating series test has we need to satisfy two conditions. So first off, I'm saying that a sub n is greater than 0. So different books, different instructors will define the terms of the series differently. And I'll talk about it in just a second after we write our test. But I just want you to pay attention to how we're defining our test. So if a sub n is greater than 0, then the series n equals 1 to infinity of negative 1 to the n a sub n and negative 1 to the n plus 1 a sub n converge under two conditions. Our first condition is that the limit as n approaches infinity of a sub n has to be 0. And our second condition is that a sub n plus 1 is less than or equal to a sub n for all n. So what I was talking about here is the way that we're defining our alternating series test. The a sub n is only the magnitude of the term. We're not looking at the sign at all. So we're not interested in the sign of the term. So we're only looking at the magnitude of the nth term. So our definition, it doesn't include the sign at all. So we're ignoring that. So our nth term, we want to separate it out so that we have some positive quantity here, and then we deal with our alternating signs separately. Some books do it differently. Some books deal with the absolute value with an absolute value in there. I just want you to be aware of how we're defining this. So the first, just to note that the first term is related to our nth term test for divergence. If the limit of as n approaches infinity of a sub n isn't 0, then our series diverges. So that's our nth, kind of related to our nth term test. So these are the two conditions under which alternating series converge. So let's look at a couple of examples of using this test. I'm not going to go through the proof of the alternating series test. But essentially this has to do with the terms being, the sequence of partial sums being bounded and monotonic. It's what these conditions guarantee. So let's look at a couple of examples. So we have the sum n equals 1 to infinity of minus 1 to the n plus 1 over 2n minus 1. And I'm just going to write out a few terms, just so we see what this series looks like. 1 minus 1/3 plus 1/5 minus 1/7 plus dot. So here's our series, and we want to test this for convergence. We're going to determine if this series converges. So my a sub n here, the way we've defined our a sub n is going to be 1 over 2n minus 1. And then I need a sub n plus 1 for my test. A sub n plus 1 is 1 over 2 times n plus 1 minus 1, or 1 over 2n plus 1. So for our second condition, we need to show that a sub n plus 1 is less than or equal to a sub n. So what we're trying to show is that 1 over 2n plus 1 is less than or equal to 1 over 2n minus 1. Is this condition true? Yes.
Well, it is, but you for the a sub n, you should take less than negative.
Yeah. So yeah, for the a sub n, we're not worried about the alternating part here. We're only looking at the positive part. So some books do it differently, some define that a sub n differently, but the way we stated it, we're only looking at the positive part.
Oh.
So are we satisfied that this condition holds? Is 1 over 2n plus 1 less than or equal to 1 over 2n minus 1? We're satisfied that that holds? If we weren't sure, we could say we know that 2n plus 1 and these are positive. If we weren't sure, we could cross multiply and say is 2n minus 1 less than or equal to 2n plus 1. And we know that that's the case. For n greater than or equal to 1, this is true. So that condition holds, and is the limit as n approaches infinity of 1 over 2n minus 1, does that equal 0? Yes, we know that's true. So the series converges. Let's look at another example, a little more complicated. So we used our alternating series test. We showed that this series converges. So our second example, a little more complicated. So let's look at the sum, n equals 1 to infinity, of minus 1 to the n, times n over 2n minus 1. And a couple of terms of our series: 1 minus 2/3 plus 3/5 minus 4/7 plus etc. etc. So there's our series this time. So our a sub n, we're just looking at this positive part. A sub n is going to be n over 2n minus 1, and we need to compare that with a sub n plus 1. So I get n plus 1 over 2 times n plus 1 minus 1, or n plus 1 over 2n plus 1. So for our test, for the second condition of our alternating series test, we need to see is n plus 1 over 2n plus 1 less than or equal to n over 2n minus 1 for all n. So I'm going to put a question mark here. Well, looking at those fractions, that's not entirely clear, is it? So we have a little more work to do. So I'm going to get rid of these. I'm going to clear the fractions. So we're going to say is n plus 1 times 2n minus 1 less than or equal to n times 2n plus 1. Still not entirely clear. So let's distribute here. So I get from my left-hand side, I get 2n squared plus n minus 1. And we want to know, is that less than or equal to, when I distribute here, I get 2n squared plus n. And this clearly is less, this quantity is clearly less than this quantity. So the second condition holds. Now let's look at our first condition. We want the limit as n approaches infinity of n over 2n minus 1. What is that limit? What is it? 1/2, right? So, but the important thing is it's not 0. So this limit is not 0. So the series diverges. Yeah, you could do this. You could do this test in the beginning. I wanted to go through this process just to illustrate that when this inequality, if you do have to work with this inequality and it's not clear, then you have to do a little more algebra to make sure that condition holds. If the limit was 0 and we had to do some work here, I wanted to show that.
But it's probably just like in general, it's probably trying to reach the limit of 0 before you do all of it.
If the limit's easy to find, then do that first test first. I just wanted to, like I said, wanted to show that sometimes we have a little more work to do to establish the inequality. So the series diverges. Oh, you want the exclamation point? There you go. Series diverges. All right, let's look at yes.
So A sub n diverges, so just use the alternating series.
No, the alternating series diverges because both conditions have to hold for the series to converge. We have to have this inequality hold, and we have to have the limit as n approaches infinity, the nth term be 0. So both of those have to be true for the series to converge. Okay? All right, let's look at something that's going to lead us into another topic. Sum of n equals 1 to infinity of minus 1 to the n of 1 over n. This is the alternating harmonic series. So we're going to test this alternating harmonic series for convergence. We have a sub n is 1 over n. So let's do our first test first. We know that the limit as n approaches infinity of 1 over n is 0. So our first condition holds. So we did the easy one first. And a sub n plus 1 is 1 over n plus 1. And 1 over n plus 1 is less than or equal to 1 over n for n greater than or equal to 1. So our alternating series, this tells us our two conditions hold for the alternating series to converge. The alternating harmonic series converges. And there you go. The series converges. But we know the sum n equals 1 to infinity of this, the absolute value of this, which is just the harmonic series, diverges. We've proved that directly. So we know this alternating, the harmonic series diverges, the alternating harmonic series converges. We call this kind of convergence absolutely convergent. I'm sorry, not conditionally convergent. So this is an example of a conditionally convergent series. So when we have the alternating series converge, but the absolute value series diverge, we call that conditionally convergent. So the alternating harmonic series is an example of a conditionally convergent series. So let's talk about conditionally convergent series for a second. So, we're going to talk about conditional and absolute convergence. We saw the alternating harmonic series. We said that was an example of a conditionally convergent series. We're going to say the theorem here. If the sum n equals 1 to infinity of the absolute value of a sub n converges, then the original series, also converges. So note that when we're testing this absolute value series, when we're taking the absolute value of the series, we can use all of our other tests that we've already talked about for series. So this series, the absolute value series, is going to be positive, so we can use all of our other tests. And when the absolute value series converges, the original series also converges. And the converse is not true. And the alternating harmonic series is a counterexample that shows that this converse is not true. The original series, our alternating series converged, the absolute value series did not converge. So the alternating harmonic series is a counterexample that for the converse of this theorem. And the proof of this theorem involves just manipulating the absolute value and showing that if this converges, that it places a limit, it places a bound on this series, and so that one also has to converge. So using this theorem, we have a couple of definitions. So our first definition is absolute convergence. Absolute convergence is, we say that a series n equals 1 to infinity, and here I'm saying that a sub n can have positive and negative terms. Forgot my E. So our series is absolutely convergent if the sum n equals 1 to infinity of the absolute value of a sub n converges. And our conditional convergence a series is conditionally convergent if the sum n equals 1 to infinity of a sub n converges, but the absolute value series diverges. So this is conditional. That would be an example of conditional convergence. And the alternating harmonic series would be a conditionally convergent series. Because our alternating harmonic series converge, but the absolute value, which was just our normal alternating series, or our normal harmonic series, diverge. And just to be clear here, we're saying in our definition of conditional and absolute convergence that a sub n, our terms can be positive and negative. So questions on conditional and absolute convergence. So a lot of times when we're working with alternating series, we have more work to do. We want to see if the alternating series converges, and we might want to determine whether or not it's absolutely or conditionally convergent. So let's look at one more example, and then let's see. I have a little time. I want to talk quickly about the alternating series remainder. So let's look at the sum n equals 1 to infinity of minus 1 to the n over n squared. So we want to test this for convergence, and we want to see if it's absolutely or conditionally convergent. So let's apply our test. A sub n is 1 over n squared for our alternating series test. A sub n plus 1 is 1 over n plus 1 squared. And we can see right away that the limit as n approaches infinity of 1 over n squared equals 0. So our first condition holds. And we want to know now is 1 over n plus 1 squared less than or equal to 1 over n squared. So does that inequality hold? Yeah. This is going to be, n plus 1 is going to be larger than n for n greater than or equal to 1. So this holds. So our alternating series converges. So let's look at the absolute value series. So we're going to look at the sum n equals 1 to infinity of the absolute values minus 1 to the n over n squared. And this equals just the sum of 1 over n squared. Does this series converge? Yes? What kind of series is this? This is a P series. With P equals 2. So this series converges. So both series converge. So this is an example of an absolutely convergent series. So our original series, our original alternating series is absolutely convergent. Let's look at an example of a series that's a little trickier. Let's look at the sum n equals 1 to infinity of sine n over n squared. So our series is going to be sine of 1 plus sine of 2 over 4 plus sine of 3 over 9 plus alpha dot. Can we use the alternating series test on this? Katie says no. Why? Does it have positive and negative terms? Is this going to have positive and negative terms? Yeah? Are they going to strictly alternate? Not necessarily. So we have positive and negative terms, but they don't strictly alternate. So this is not an alternating series. It has positive and negative terms, so it's not an alternating series. We can't use the alternating series test. How are we going to test this for convergence? Should we test the absolute value? So let's look at the sum equals 1 to infinity of the absolute value of sine n over n squared. What can we say about this series? It's going to be less than or equal to this series is going to be less than or equal to what series? What does the sign of n vary between? Negative 1 and 1. So the absolute value of sine n over n squared is going to be less than or equal to 1 over n squared. Because the sign of our value is somewhere between negative 1 and 1. So when we take the absolute value, we get some fraction. The maximum it's going to be is 1. So this series is less than or equal to 1 over n squared, which is, we just said, is a convergent P series. So our absolute value series is convergent by direct comparison. And so since the absolute value series converges, our series converges absolutely, and our original series also converges. The series is absolutely convergent. And the original also converges. So we had to be a little trickier with this one. Any questions on this? Did I misspell something?
No.
You're just making fun of my handwriting? Which particular part? My E? Yeah, I kind of. How do I do that? I need to concentrate more. When I stop concentrating on my writing on this thing, it gets really bad. When I concentrate more, it gets better. So really quickly, I want to say something about the absolute value, the alternating series remainder. So if we want to estimate something with the sum of an alternating series, if we have some convergent alternating series, we want to use the nth partial sum as an approximation. The error in that approximation is less than or equal to our first neglected term. I'm not going to do a lot with the absolute value series, with the alternating series remainder. Just know that if you're estimating some value with a convergent alternating series, your error is less than or equal to the first neglected term. So if you're summing from 1 to n, your error is going to be less than or equal to the n plus first term. And I think there might be one homework problem that asks you for an estimation. Just know that your error is less than or equal to that first neglected term. But I'm really not going to do a lot with the absolute value series or alternating series remainder. And I want to mention really quickly, this isn't part of what we're doing. It's just a really interesting fact about conditionally convergent series. So this is just something that I find very interesting. We can rearrange, if we have a conditionally convergent series, George Riemann proved that you can rearrange the terms of a conditionally convergent series to produce any sum. You can choose any sum and you can rearrange the terms of a conditionally convergent series to get any sum. So I want to show you really quickly. If we show later when we talk about power series, we're going to show that the sum n equals 1 to infinity of minus 1 to the n plus 1 over n, which is I'm going to write as 1 over 1 minus 1 over 1/2 plus 1/3 minus 1/4 plus dot dot dot. This equals the natural log of 2. We'll end up showing this a little later. I'm going to rearrange the terms. So I'm going to rearrange them 1 minus 1/2 minus 1/4 plus 1/3 minus 1/6 minus 1/8 plus 1/5. I'm going to write a bunch of terms here. Minus 1/10 minus 1/12 plus 1/7 minus 1/14. So I'm just rearranging the terms. And this is 1 minus 1/2 minus 1/4 plus 1/3 minus 1/6 minus 1/8. So we're just being clever here in how we're rearranging them. Plus 1/5 minus 1/10. It doesn't look clever right now, but minus 1/12 plus dot 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 And now I'm going to sum up these in the parentheses. This is 1/2 minus 1/4 plus 1/6 minus 1/8 plus 1/10 minus 1/12 plus 1/14 minus dot dot dot. This equals 1/2. 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 minus dot dot dot. And this is 1/2 of what? What we started with. So we can rearrange the terms of this series to come up with half the sum that we originally that we proved that the sum was. So so if we rearrange the terms of a conditionally convergent alternating series, we can get any sum that we want. So you cannot make arguments about rearranging the sum of a infinite alternating series and say you get some different sum. That's one of the strange, interesting properties of alternating series.
And it only works with alternating series.
With conditionally convergent alternating series. Now we could rearrange a finite sum and come up with a different result, and that would be okay. But we can't rearrange an infinite sum. Yeah, Ann. Yeah, we can rearrange it to get. That's what George Riemann proved, that we could rearrange this to get any sum we wanted. No matter, we could pick any number and rearrange these terms and get any sum. There's an article in your book on page 636. It links to an article about this process that gives a really good explanation of it. It's a really fascinating thing. So, anyway, homework.
Now we'll take a step to figure that out. We're going to put it this way. I want to do that. Possible other things in mind. Yeah, don't give it.
There you go.